Hello everyone, welcome to EduCell. Today's topic is asymptotic notation. We are going to read the asymptotic notations, why it is being used, and how we will rename suppose complexity is playing a vital role. Then how to define, right? That part we will discuss, and what is complexity, then what is time complexity, then what is space complexity, then how it will be defined using any method that we will discuss, and increasing order of the space complexity and time complexity will be discussed, and also the graph how it will be look like that we will be discussing that one. Next slide is time and space complexity. Always remember, complexity means needed to complete a task or needed to complete a problem. We are ultimately providing the solution. That's why we need time and space complexity. Okay, because certain time is needed to complete a task. Definitely, you can say why algorithm is used, why algorithm is important. For that case, always remember one thing: we know our time is very limited, we know the space is limited, also others are limited also for us, peripheral of the system is also limited, everything is limited. But why we're focusing time and space? The main reason is, if you are actually writing a solution for a particular problem, here the problem is playing a vital role, then how you are writing the solution, the writing steps are considered as algorithm. Okay, then that algorithm, whether it is taking less time to solve the solution or solve the problem or not, whether the solution you are actually providing, is it really taking less space and less time to provide the answer or not. If it is doing that thing, then we can say it is an effective algorithm. So once you can say it is an effective, first of all you have to compare with an algorithm. Means if similar algorithms are there, like all algorithms are suppose finding the same solution. Suppose you are finding odd and even number. Suppose even number you are finding whether a number is even or not. There are many codes could be written. Okay, so in that case, the code which you have actually written like pseudo code, a false code you can say. If you have written a false code, like your false code is different, their other false codes are also different. In that case, your target is, if your algorithm is taking less space and less time as compared to others, you can say your algorithm is effective. Otherwise, if there is no other competence of your algorithm, you can say your algorithm is best algorithm or suitable algorithm or you can say effective algorithm, because you cannot compare with anyone. Though you cannot compare, so you cannot say it's whether it is effective or not. So in general, like it is written everywhere, like complex the algorithm complexity should be less. But how do you say the complexity, if you are getting at least suppose log n, if you are actually reducing towards the log square n or log cube n of it, so definitely you can say somehow you are reducing the time complexity, or instead of the space you are actually reducing. But without having any other options, you cannot say your algorithm is effective or not, because there is no other way to compare. Comparison must be there to say effective or not. Okay. Next thing is, you can say algorithm is used to, in my words, basically, I am saying the definition of algorithm is it's effective use of artificial resources. You can say why I'm saying artificial resources, because time and space is defined by us, so it's a resource for us. Time is also resource for us, though we are writing it. So these two resources we actually generate from our end. So it's artificial resources, that like natural resources is your you can say the petroleum. Okay, so the demand is high, the price is also high. If demand is low, price will be low, like this. Okay, so though it is resource for us, like it is not widely available, that's why we are saying petroleum is a natural resource. Like this, the space we generated. And why we are saying it is limited, because if you are paying more, then the space could be more. If you are paying less while purchasing the system, that time space will be less. So that you need to manage the original RAM space, because RAM, random access memory, is helping you to run the to store the current program there. So that is why you need it. Okay. And also sometimes you are using the some part of the hard disk, or you can say solid state device or HDD, whatever that you are using. Some space are getting used, but maximum space actually we are following the RAM, random access memory. In case of mobile phones also, same thing happened. RAM is there as well as ROM is there. Okay, so we are trying to managing those spaces as well as the time. Why time is important? If you can say, if I want to find any number, whether it is even or not, we know is you can divide by 2. If it is taking 2 days to find a number is even or odd, it's better not to go for it. So your target is within certain time, within a fraction of time, at least you should deliver it. So that's why time complexity and space complexity is playing a vital role. Time and space basically. Then what do you mean by complexity? Complexity is, in simple word, needed to complete a task. Needed to complete a task is complexity. You can add time there. Time complexity is time needed to complete a task is time complexity. Space needed to complete a task is space complexity. Suppose some space are needed to complete a task, that time you can say space complexity is this much. Like, to reduce space complexity will be better for us. If space is taking 1 GB, space complexity is 1 GB, you're trying to reduce it to 100 MB, suppose. That is how you are actually reducing the space complexity, means you are enhancing the effectiveness of your algorithm. Okay, so that's why we want the reduction of complexities through which we can enhance the efficiency of our algorithm. Okay, or effectiveness of our algorithm. So it's a very good definition. You remember, time needed to complete a task is time complexity. Space needed to complete a task is space complexity. The information, the definition is written here. Okay. So next slide is asymptotic notations. You may ask me why asymptotic notation is important. Like, I can tell you an example. To measure the distance, we are having kilometers, we are having meter, we are having centimeters too. Okay, so through that also we can have to find out the information about the distance. Also light year is also used there. Then can we use only one unit to measure everything? I must say no, because one unit if you are keeping, so there you have to focus on the like point value or decimal value, you can say, like instead of saying it's 1 kilometer. Okay, if you want to use only meter as a variable, then meter case it will be 1 meter, suppose you are taking 1 meter. But in case of kilometer you have to write 1000 meters. Like this you have to at least fix of your distance. Okay, so this is how actually the problem is around us. So to define the bigger one, we know the lower one of the meter is centimeter, the upper one is the kilometer. Okay, like this we have kept the units, okay, to measure it in a well format. Now you can say, like this, the complexity is also being measured. The lower one, higher one, middle one. Like this, the units are being decided. So that is why we are reading the asymptotic notations. You can simply say it's a unit, because though we are focusing on algorithm, that is why they are saying it is asymptotic notations. Otherwise, you can say it's a unit of finding the complexities basically. Okay, so how to measure the complexity? We need a unit. That unit is asymptotic notation. Okay, now you can focus. In simple word, I can tell you how to define the cases. Suppose you are having one class and your suppose your home and that side your institute. Okay, the distance between your home to institute is suppose 2 kilometer. Okay, and based on the speed you can reach within the time. So I am just writing it with the speed one side and time another side. Okay, which will be giving you the correct idea, like when we are picking as a best case, worst case and average case. Based on that we will define the notations. So suppose speed is 120 kilometer per hour Second speed is 60 kilometer per hour. Third is 30 kilometer per hour. Okay. The time it is taking, if 60 kilometer per hour, we know it is 10 seconds. Okay. Like 60 kilometers, 2 kilometer you have to go with the 60 kilometer per hour, then it will take 2 seconds. Okay. So if you increase the speed, definitely you'll reach within a time. So you are increasing two times, so you have to divide with the two. So 1 second only. If you're reducing by 2 kilometers, you are enhancing the time there, which is suppose 4 seconds. Clear? So sorry, not seconds, it's minutes. Okay. So within 2 minutes you can reach, because 60 kilometer per hour, that I forgotten, 60 kilometer per hour that you are using means 1 kilometer, to cover 1 kilometer it will take 1 minute. To cover 2 kilometers it will take 2 minutes, not seconds. Okay. So what exactly we have to do here? Which one is good and which one is best? Which one is the worst, best, and average case? We have to first measure it. If I'll tell, out of this, if we focus on time, the less time will be effective that we studied. Here, the less time is 1 minute. Okay, na? So 1 minute we can say it could be a part of best. But as for the real life, this is not best. If you are focusing on the real life, if you are running with the 130 kilometers, might be are actually you might approach to an accident. So that's why it's not good for the real life issues. So we can use this in algorithm, like which one is the best case, which one is the worst case for us. So here I'm writing cases. So here it is best case, and I have two other options also. If I compare with this, the maximum it is taking, so that's why I can say it is worst case for me. Worst case means it is taking 4 minutes. Though it is safer for us in a real world, a real life, it is good for us in a real world. Okay, so but it is taking 4 minutes. Next, best and worst we found. So anything within that range, we can say it's an average case for us. So here, this is the in between both the best and worst. We are saying this average case for us. Okay, just I am writing ABZ. Okay. So these are three cases we defined as per the speed. Like we know time is less, so we should pick this as our worst time complexity, or best time complexity, or average time complexity. Like this, here these two notations we are using as best case. While we are finding the best case, that time we are applying these notations. Suppose sometimes you can see omega of 1, it is the best case always. Okay, I'll also discuss why worst case is always being taken, that I'll tell you with a proper example. Okay, next, these two big O notation is considered as worst case notation, and this theta notation is your average case notation. Okay, average case notation. So best case, average case, and worst case. Simple question, why worst case is taken then? The main reason of taking worst case is, you know, if you're reading well, you will definitely get pass in an exam, that we know. Okay, if you will be very serious in your class, definitely you will get O grade, or might be you will be topper inside your class. In your class, suppose you will be very serious, you will be topper. If you are just normal, you will get passed from this. Or if you not read anything, okay, so you'll definitely fail. This is your worst case condition that you know. But always we are not in best case, because we know if a person is serious, he must be a topper. If a person is not serious, that is why we are focusing on which case, the worst and average. But basically worst will be our main target, because if you are not reading anything and you are getting pass marks, that is why we need from you, like you have the capability, you have the caliberty that you are getting pass marks without reading it. The worst case means how much that you are giving effort and you are getting it. Okay, And one more example I'll tell you. Like in general, we are making friends. हम जब दोस्त बनाते हैं, हम उस टाइम क्या सोचते हैं कि भाई साहब ये आ, इतना तक हम इसको झेल सकते हैं. We can at least observe his words, ornamental words. You can say the कुछ भी बोल रहा है भैया, गाली दे रहा है या कुछ भी दे रहा है, we can at least इसको सह सकते हैं कि हाँ, up to this we can maintain a level. Okay, like everyone in our life. So जब किसी को हम दोस्त मान रहे हैं तो हम मानते हैं कि एटलीस्ट लाइक अस, और माइट बी कुछ बुरा है तो इतना तक बुरा होना चाहिए, नहीं तो उससे ज्यादा होगा तो दे आर नॉट आवर फ्रेंड्स. मीन्स वी आर एक्चुअली फोकसिंग ऑन द वर्स्ट केस. Worst case is actually focused by us, which is bigo. Okay, and simple. You can ask me why bigo is always being used, sir. Why not little o? There is also example I'll tell you. Little o is you will in future will see the mathematical equations there. Little o is strictly greater than the c of gn, which we will discuss that time. I'll tell you the why it is not actually being used sometimes. It is strictly greater, uh, and big O is strictly greater equal to also there. Greater than equal to, the greater than equal to sign is getting used in an big O condition, but little o only strictness is there. So in general, if a teacher is very strict, okay, is one case. Second case is if a teacher is strict as well as friendly in nature. So all will follow the strict with the friendly teacher rather than the strict teacher only. A strict teacher, nobody is exactly are interested to read or might be follow that person because he is strict. Okay, that is why the main reason behind it is if sometimes we are getting some time complexity which is equivalent to suppose n. In that case, if we are using big O, no, sorry, small o notation, which is little o notation, that time what happened, like in that little notation it will only be strict to this one. Okay, like it will not accept if you are having if you have just used plus 1 or plus 2 or plus some constant if you are adding. So no, it will not take it. It actually tells you no, it will accept if you have linear time complexity. Suppose n is there, then only it will accept it. It will not accept if you are having plus c. Okay, a plus constant suppose you are adding n plus 1 suppose you are having, so before that it has some condition with the n, so it will not accept. So strictness is not always good. So whenever a teachers, some teachers are also reading on this video, that time it's a suggestion from my end, you should be always big O rather than a little o. Might be some problems could arise in future, so this is why we are actually using a big O notation. Now switch to the next slide where actual conditions will be happened. Here the big omega notation, which is actually accepting this one, c of gn is less than equal to f of n. This is big O notation. Okay. Suppose for little o notation, that should be c of gn will be strictly greater than f of n. It will not accept equal to sign in case of little o. Okay, in case of little o notation, then what is n and what is n naught, that we will discuss, and what is c we will also discuss. These are the theory, so it is being written. So if I'll read it, it could be a translation type of thing, better you go through it. So I'll just discuss on the part like exactly where we should focus. You can say the functions, there are two different functions. The first, our target is suppose our function will be f of n, and we are getting functions which is g of n, and it is getting multiplied with a constant where c is a constant. It is written c is a constant, n naught is also constant, or n0 you can say it's a constant. So up to this, like up to this n naught, there might be a variability of f of n. Okay, like sometimes you can see 14 this side and 4 n this side. In this case, we are choosing n as our maximum time complexity. Sometimes that n y because it is variable, but if you can take 1, then 4 into 1, which is 4, 4 is less than 14 now. Then why you are picking this as your big O notation? The main reason is it might be having certain range. N equal to 2, that time it is 8, less than 14, not an issue. You can also go for it n equal to 3, which is 4 into 3, 12, also less than this, it's okay. But one time will come where n equal to 4, okay, that time what will happen, n, that 4 which is that you have already as a taken as a constant that you keep, and in place of n I'm just writing it here, it is 16, which is not equal to, which is not equal to 14. From 4 onwards, your value towards infinity will have to follow your function, which is a function that it is, okay. So in big O notations I'm telling, in big O notation, which is represented as this big O. In big O notation, you remember that in value means your C of Gn will be always in a higher condition than your function. Okay, so this is what n naught is. Okay, that n we are actually taking is n naught. Up from this n naught, whatever the value that you are getting, you will have the proper condition. If it is omega, like we are discussing of the big O, which will be discussed in the next slide. But at least for like those who have already seen like how to find a time complexity, for them it is quite easier. Those who are new for this video, don't worry. Actually, for them I'm just trying to manage, because you will be reading other videos too. That time, whenever you will get to know like why this, why that, that time you can correlate what exactly the n naught is. N naught we are saying as a part of constant, but it is somehow we can say it varies, but up to certain point it will be less than a certain constant, or might be some value which will be added at the back of it. Like whenever we are saying which one is bigger, that time up to certain point might be it is lesser to the previous one, but after certain time to infinity we are having a range of data. Within that data, the condition will fall good, like f of n should be greater than c into g of n. So up to n naught might be there will be a variability of the results. After that, there should be a constant growth of f of n as well as c of n. Might be here we are discussing about big O notations. In big O notations, our functions will be greater than of the c into g of n. Whatever the value you can enhance, not an issue, but that should be less than f of n. So this is what it is written in big omega condition. So like theta condition is, before theta condition at least we should discuss the big O. So here in big O condition, f of n will be less than that c of gn. Okay. So here for the condition I can tell you, which I told you before, here it is strictly greater than c into g of n in little o condition. Okay, so here in this it's not little, it's little omega. Okay, for little omega the same condition, you just remove the equal to sign there, they are only strict. Okay, so f of n is greater than there, here f of n is less than here, so which is little o condition or little o notations. Okay, so though there is a equal to sign we are using, we can say we should accept it. Same condition here might be the problem like which we discussed earlier. Up to this might be hurdles could be there, but after that everything will be on a certain point. Like if the growth will be there, so growth should properly follow the condition which we have written. Okay, so this is how we should represent what is n naught, what is c. Okay, sometimes we are reading from the internet, but we cannot understand. That's why I'm actually going for the video lectures. The main reason behind it is why we are using it. If I go in a streamline, I could be a translator, like nowadays the people are doing. Do not be a translator, be like a teacher. What you understood might not be understood by all. So how you are actually being a proper, like big one, okay, big of one, like on constant, be like a constant, like what you are actually delivering that should be understood by all. Okay, that is what my target is. So here this video is all about like big O notations. Next, big O notations, you can say this is a part of big O notations, and this part is omega notation. So this is your average case. Okay, this is your average case. Like this case, you can see here f of n is greater than c of n, but when c2 is getting added, it should be greater than this. Okay, so this is how we are actually defining the conditions. You can see the same conditions which I told you. Okay, this O condition, like C of Gn is this part is your big O notation, this part is your big omega notations. Okay, the combination of this is average case that we recently discussed with an example like 60 kilometer per hour. If a person is riding, that time it will take 2 minutes to reach the destination. Your institute, suppose you are running towards the institute, that time you can definitely meet your expectations. So within that, whatever the conditions we are having, that we can consider as a average case conditions. So I hope you understood. Next, we are actually focusing on increasing order of it. Like in general, many people are actually facing the issue. So the first is the constant. You can remember this as your constant time complexity or constant space complexity. Better you should stay it. It should be constant. Okay, constant always less than everything. Now you focus log base 2, base 3, there are many things, but I should be very precise enough. If log 3 is there, so log 3 will be definitely less than log 2. Okay, I'm just writing it log 3. Uh, you can say log of 3, anything. Better we should focus on 2, or you can say log 3 n. Okay, if I'm writing, it should be less than log 2 n. Okay, this is one part of saying the increment order, as well as the main thing which we actually are going to discuss is remember that one log. Remember all are base 2. Okay, don't worry about bases now. Just log are getting the number of logs you are adding, that will be just bigger than the constant, but that will less than the big of log n, because the number of logs you are using, that will be reducing one by one. So for that reason, I'm just saying this is your logarithmic complexity. Okay, next, instead of writing this one also, you can say if constant is on like log square, if 2 times log are there, log square n, log cube n, like this. Okay, next is big of n to the power anything. Suppose n to the power 3 I'm writing. Next will be big of n to the power 2. So this is how you are actually defining it. Okay, this is what you are defining the complexities. Okay, so these are roots. Okay, cube root, square root, like this. Next, once it is done, next will be your linear. Okay, you should know like how we are actually defining it. Next, once linear is over, linear will be less than which one? If n will be multiplied with log of log n, if you can say this one also, it will be greater than the log. So simply I'm just writing n log n. Okay, so if I'm taking this one, this will be greater than the n. So if n1 is asking, so there is big of n log square n, another side is log n, which one is greater than, ऐसे कोई क्वेश्चन पूछ लिया, then if anyone is asking, so log square is simply you can check n log of log n. So I told you, if number of logs are more than only single log, then definitely it will be less than single log, always greater, and number of logs you are using, it will be lesser. Okay, so log square will be less than n log n. Okay, So these type of questions could be arise. So don't worry. If you are actually not able to find it, simply put the value of n as 2, 3, 4, 5. Like though you are using log, if base is 2, so better you work with the 8, 4. Like you can easily find which one is greater, which one is not greater. Suppose I am asking whether n log n, the same thing we will discuss now, log square n. Another side is which one is greater. Suppose I'm asking, you can take the value, don't worry about it. Okay, now I'm just taking the value is, suppose n is 4. In this n is 4, what I'll find, big of n which is 4 that I'm writing, and here log of log 2, 2 4, instead of 4 that I'm writing 2 square, here I'm writing 4 now. Okay, so in this 4, next will be big of 4 cross log 2, log 2 to the power 2. The 2 to the power 2 will be reaching here. Okay, you can now write big of 4 cross log 2 to log 2 base 2. Clear? So log 2 base to 1. Now log 2 base to 1. So यहाँ पे what is the answer now? Big of 4. Or you remove big O, don't worry about it. Remove big O for a while. That could be very easy to understand. What is the value now? 4 is the value. Okay. Here, if you can take big O, n is 4, log 4 base 2. In that case, what happened? Big O 4 into log 2 to the power 2, 2. Okay. Then big O 4 into 2, which is big O I'm removing, sorry. Don't be confused. Okay. Because confusion will be creating easily. Solution we may not get easily. Okay. In this case, 4 into 2 and log 2 base 2 is 2, so which is 8. So here the answer you are getting by applying n as 4 is 8. Here you are getting as 4. I told you the number of logs you are using, indirectly you are reducing it. Simply put the value. Okay, so I think it's understood by you. Don't worry, like like take the value as anything. I know I told you variable. The variable means it should have some number, no? Definitely it is variable. Otherwise, if it is do not have any number, only one number will be accepted, then it should be called as constant rather than a variable. So from this we can easily understand the complexity part. Okay, so what we will say, it should be said as linear is added or linear is multiplied with the logarithmic, so it is said as a linear arithmetic. Linear arithmetic. Okay, linear is there, linear is there, and so we should say it's linear arithmetic. Linear with arithmetic, logarithmic. Okay, next, big of n square, next big of n cube, like this. The number of constants you enhance, the power also it will be enhanced. Okay, it's quadratic basically, or sometimes we are saying it is polynomial. Better you should say it's polynomial. Okay, polynomial time complexity could be anything. So polynomial means n to the power something we are writing, n we are writing, and power is some constant, it should be polynomial. Okay, representation of polynomial is big of n to the power k, which is where k is constant. Okay, so it is polynomial. Next, exponential, 2 to the power n, we go 3 to the power n, like this. It is exponential. Okay, exponential, it could be represented as some constant to the power n is called as constant. Okay, constant to the power n, if you are writing, that is called as exponential. Next, we go n factorial, and last is n to the power n. So this is factorial, and this n to the power n, all are maximum portions I have seen, they are saying it is super exponential, which is a wrong concept you are delivering. Why it is not super exponential? Is it constant? The n you are using, it's not constant always. It's not constant, by the way. N is variable, n is linear. And n to the power something, if you are saying n to the power constant, if you are saying it is polynomial. But you should say it is super polynomial. It should be said as super polynomial, because maximum professors outside India, inside India, the uh, those who have experienced more than few years, like 25 years, 17 years, or more than even if 50 years of experience in this algorithm, they said it well, that it is said to be super polynomial rather than super exponential. Why? Because polynomial you are using, upper that one you are taking as the variable which is n now. So it is super with the polynomial. That's why it is super polynomial. It is maximum complexity. You can say if it is time complexity, it's maximum time complexity. If it is space, the space maximum space complexity. So maximum space complexity could be like it is taking huge space, or it is a loop space. If it is taking, could be written as super polynomial, or else infinite loop. In that case, if you're finding the time, taking more time, so it is super polynomial. For infinite loop, the time complexity is super polynomial, because you cannot define within this time. So maximum time it is taking, so which you cannot vary, you cannot define it well. That time you can say it's a super polynomial. Next slide is all about the chart, how it will look like. You can say the constant will be, direct line will be the constant. Little bit upper to the constant is log n, and then straight, like it will be for n. Here the chart is ready. Like all we are doing the same pose, but we don't know which one are the pose exactly. The pose is n. Like for each value, the variable, like if you're taking 20, if you're taking 10, like this, it will be like up towards, diagonally, you can say it will reach. So big of n. Next, for n log n, quite higher than the n. Now n square is quite higher than the n log n. Then n 2 to the power n, or which is exponential, is quite higher than the polynomial. Next, n factorial. Then this one, not like this. Some you can say some time which is maximum than this n factorial is n to the power n. Okay, this is how it look like. But in general, maximum people are saying n factorial is n to the power n. Also sometimes we are discussing while we are actually approaching for the recurrence relation. That time you can get the video on this one. Okay, so where we should assume that n factorial could be considered as n to the power n. Okay, so here the constant will be like, it will never change the directions. Next, n square will be like this, log n like this. So these are the it will look like this, like these are the chart. If the value will be changed, how the graph will look like. Okay, so here this is the example which we discuss about the complexity, where we discuss time complexity, space complexity, everything in increasing order also we discussed with a chart. So I hope it is understood by you. Thank you for watching. Have a great day.